So we all know that toast always lands butter side down, and cats always land on their feet. So I wonder what would happen if you like strapped a piece of toast on the back of a cat and dropped it. On the other hand, you have different fingers. Good. Awesome. Okay. The last video for Unit 6. This is Unit 6, Section 6. By the way, I did not do a video for Section 4, so you'll need to go check out the completed notes online if that's what you're here for. But we're going to get right into Section 6 here and try to forget about my stupid jokes. Here we go. All focused and everything. Now in Section 6, we turn our attention away from quadratic functions for a moment, and we look at square root functions, which are the inverse of a quadratic function. And we're going to get into that a little bit later. But for now, let's just kind of look at some square root functions a little bit. Okay, so it's going to ask us here to kind of plug some numbers into a square root function and see what we can do. So we've got our function here, and we're going to plug in some x values. Now, if I try to plug -3 into this function, -3 plus 2 is -1, and I'm doing the square root of -1. And even though we know how to handle imaginary numbers, we're not going to be able to graph that point here on the graph. So this is just to remind you that when we start working with square root functions, the domain is no longer all real numbers, that there are actually numbers that are not included in the domain of the square root function. So -3 is not in the domain of this function. We'll get a little bit more serious about finding the domain here in a little bit. If I plug -2 into this function, I'll have the square root of 0, which is 0 plus 1, and I get a 1. If I plug -1 in there, I will get 1 plus 1, which is 2. If I plug in 2, I'll get square root of 4, so that's 2 plus 1, which is 3. If I plug in 7, I'll get 3 plus 1, which is 4. Now you'll notice that my x values were very strategically chosen here so that when I plugged those numbers into the function, I got nice, easy y coordinates. And so if you're going to graph a function this way, you have to be a little bit strategic about how you choose those x coordinates. Okay, let's go and plot these points. -2, 1, -1, 2, 2, 3, and 7, 4. And our square root function looks kind of like that. And this is absolutely, it is half of a parabola. It's just turned on its side. Okay, it is, and that's because it's the inverse of a quadratic function. So this is indeed half of a parabola just laying on its side. It asks us for the domain here. So -2 is the smallest x coordinate of any of those points. It asks for the range. This point has the smallest y coordinate, which is 1. So we'll go 1 to infinity. Identify the coordinates of the starting point. So a parabola has a vertex, and this is kind of half of a parabola. I actually don't have a problem calling this the vertex. Throughout the notes here, they'll call it the starting point, and that works as well. So you can either call it the starting point or you can call it the vertex. Either one is fine with me. We'll notice that that's -2, 1. Notice the connection between that starting point and the domain and range there. Okay, now it's giving me kind of a basic form of a function here. Let me talk a little bit more about that. So in section 3, we kind of looked at, we remembered what happened if we start with an absolute value function and how we can move that function left and right and up and down. This one, for instance, was moved right 3 and up 2. And then we continued that idea with a quadratic function. If we start with y equals x squared, we can move that. I just moved this the same way I moved the absolute value one, just to try to make that a little bit easier to follow. But this is what it would look like if we move the quadratic function right 3 and up 2. Well, and then that led us to developing the vertex form for a quadratic function. Well, if it's a square root function, we can do the same thing. Right? We can really do the same thing. It's just instead of this quantity being squared, that quantity is going to be inside of a square root. See the relation there? It's a different shape of a graph, and actually it's not even that different of a shape, right? It's pretty much the same thing. But the form of the function is going to look really similar, okay? Just instead of squaring that quantity, we're taking the square root of that quantity. So it's saying, all right, so suppose we write, actually we have the equation of the function here. It says if this is the general form, what is the value of a? Well, if you look at the coefficient in front of the square root there, the coefficient's actually 1. So here I would say that a is equal to 1. It says, then describe the location of the first 3 points to the right of the starting point in relation to the starting point. Okay, let me talk about what they're getting at there. What they want us to do is that they want us to notice that pattern. And so with quadratics, the pattern was if you move right 1, you move up 1. If you right 2, you move up 4. If you move right 3, you go up 9. And so however far we moved left and right, we squared that, and that was our vertical change. With square root functions, you might imagine that it's just exactly opposite from that, okay? This time I'm going to go up or down first. And you know, there's different ways we can look at this, but I'm just going to stick with, if I go up 1, then I go right 1. If I go up 2, then I go right 4. And if I go up 3, then I go right 9. See how the up and down and the left and right part has kind of been switched a little bit. So up 1, right 1, up 2, right 4, up 3, right 9. There's different ways we could explain that. You know, we could go with the left, right first and just say the 1, 4, 9 pattern is now in the left, right part. Instead of the up and down, now we're doing the 1, 4, 9 pattern on the left and right movement. And then the up, down part is just the square root of the left, right movement. We'll look at a few more examples and that'll start to sink in. Okay, so set x minus h equal to, I don't think we need to do any of that part. I guess we will. Set x minus h equal to 0. If you look at the part underneath the square root, in that case it was x plus 2. We set x plus 2 equal to 0 and solve it, we get x equals negative 2. Why did they want us to do that? Well, let's hold on a second and see. Here it says to do the same thing, but make it greater than or equal to 0. Instead of equal 0, make it greater than or equal to 0. That means x is greater than or equal to negative 2. Here's what they're getting at here. And it says, what is the value of k? K is the number added on to the very end. In this case, that k value would be 1. What we're getting at here is if you take the part under the square root, set it equal to 0 and solve it, that will get you the x coordinate of that starting point. See how that gets you the x coordinate of that starting point? And your k value is going to give you the y coordinate of your starting point. I'd rather think of it as moving left, right, up, and down than just memorizing these formulaic things. The making x minus h greater than or equal to 0 and solve it, this, notice if I write that inequality in interval notation, this will always be exactly the same as your domain. Now let me discuss that a little bit. Why did we set x minus h greater than or equal to 0? Well, that's because x minus h is the quantity that's underneath the square root. And since I'm graphing these things, I need to make sure that I don't get a negative number underneath that square root. And so when I find the domain, I need to find the values of x that allow for the quantity under the square root to never be negative, meaning it'll be greater than or equal to 0. Okay. We're going to do a few more of these. And I'm not necessarily going to do every single step of this down here because I don't think it's necessary. If we plug in these points, if I try to put -5 in there, I'm going to get a negative under my square root, so no thanks. If I put -4 in there, I will get 0 minus 1, which is -1. If you plug in -3, you'll get -1 minus 1, which is -2. If I plug in 0, I'll get -2 minus 1, which is -3. If I plug in 5, I'll get -3 minus 1, which is -4. We can plot those points, -4, -1, -3, -2, 0, -3, and 5, -4. And here is my square root graph. And again, notice that this time it's just kind of the bottom half of the parabola. Okay, for the domain, now we can look at the graph and very easily see that the domain is all numbers greater than or equal to -4. And that's fantastic, but really, you know this, we need to be able to get the domain by just looking at that function. And so I'm going to use what we learned on the last page to discuss this. So for the domain, I need to make sure that that quantity that's underneath the square root, that x plus 4, that cannot be negative. Any value of x that causes that x plus 4 to be negative, that value of x needs to not be in the domain. We need to make sure at all times that x plus 4 is greater than or equal to 0, which means that x is greater than or equal to -4, and that is my domain. As for the range, let's come back to that in a second. Let's do the starting point next. This function is moved left 4 and down 1.